This eruption could become a geologic disaster overnight, and we aren't ready. If the Tonga eruption changed the way you think about tsunamis, take a second and subscribe to Orbital View. We're tracking the hazards that don't always announce themselves the way people expect, the ones that sit under the ocean, behind the models, and inside the gaps in our warning systems. And I want to know this. If you live near a tsunami coast, would your community know what to do if the first warning sign was not an earthquake? Because this story is not about a fantasy supervolcano. It is about a real blind spot. A chain of mostly submarine volcanoes runs through one of the most violent tectonic boundaries on Earth. One eruption in Tonga already proved that a volcanic tsunami can move through the ocean and atmosphere in ways warning systems did not fully expect. And the next time that happens, the people closest to the source may not have hours. They may have minutes. Let's get into it.
The volcano you cannot see, the most dangerous volcano in the Pacific, may not look like a volcano at all. No cone on the horizon, no glowing summit, no ash column rising over an island while cameras point upward and people say, there it is. It may be under the water, hidden beneath a flat blue surface that looks calm from space and ordinary from shore. It may be sitting along one of the most violent tectonic seams on Earth, inside a chain of submarine volcanoes, where heat leaks through the crust, where seawater circulates through broken rock, where magma has spent thousands of years building shapes most people will never see. And if that volcano fails in the wrong way, the first warning may not be the one people are trained to expect. There may be no giant earthquake under your feet, no long shaking, no obvious rupture, no familiar trigger that tells every coastal town, every port, every beach, every family in the evacuation zone, move now. That is the story I want to walk you through. But before we go any further, I need to be honest about the premise. There is no verified public evidence right now that a newly discovered, massive, unmapped submarine caldera in the Tonga-Kermadec zone is actively waking up and threatening an overnight disaster. I looked for that claim in official sources and I cannot support it, so I am not going to pretend it is confirmed. The real story is different, and in some ways, it is more unsettling. That phrase, published record, may sound dry, but in hazard work, the published record is where the useful fear lives. It is slower than a viral post. It is less cinematic than a secret memo. It does not give you the thrill of believing you have discovered what nobody else is allowed to know. But it gives you something more valuable, a pattern that can be checked, challenged, improved, and acted on. The published record says the region contains many submarine volcanic systems. It says Hunga produced an event that did not behave like the clean textbook picture most people associate with tsunamis. It says non-seismic sources are real enough to deserve dedicated guidance. It says warning systems have to connect volcanic information, sea level information, pressure information, and local emergency management in a way that is fast and understandable. That is not a conspiracy. It is harder than a conspiracy. It is a systems problem. Systems problems are uncomfortable because they rarely have one villain. There may be excellent scientists, good instruments, capable warning centers, and still a dangerous gap between what is detected and what the public understands. There may be a technically correct bulletin that arrives in a place where the road uphill is poor, or where tourists do not know the siren tone, or where people have only practiced the earthquake version of a tsunami drill. There may be a local leader who knows exactly what to do, but communications fail. There may be a community that receives an alert but does not believe it because the ground never shook. That is why readiness is not just a scientific question. It is a translation question. Can an unusual signal become a clear instruction before water reaches the shore? Can an abstract hazard become a practiced route? Can a community learn to act on a volcanic tsunami warning without needing the earthquake cue? Those are the questions Hunga forced into the open. Because the real story does not require a secret volcano. It does not require a hidden agency memo. It does not require anyone covering anything up. The real story is already visible in the published record. The Tonga-Kermadec Arc is a chain of mostly submarine volcanic centers stretching northeast from New Zealand toward Tonga. GNS Science describes about 80 submarine volcanoes along the Tonga-Kermadec Arc and says around 80% of them host active hydrothermal systems. That means this is not dead seafloor. It is not a quiet plain under the ocean. It is a living volcanic system with heat, fluids, chemistry, magma-connected structures distributed across an enormous region. GNS Science. Most of the time, that activity is not a disaster. That matters. A hydrothermal system is not the same thing as an eruption. A submarine volcano is not automatically a tsunami machine. Deep water can suppress some eruption styles because pressure is immense. Some underwater eruptions build cones, release fluids, create discoloration, or produce pumice without causing major coastal damage. But some do not stay quiet. And on January 15, 2022, the Pacific got a warning shot. Hunga Tonga Hunga Ha'apai erupted with a violence that still feels difficult to place inside the normal categories. The eruption sent energy into the ocean, into the atmosphere, and around the planet. NOAA's tsunami instruments recorded the event across the Pacific, and the bottom pressure recorders of DART systems captured tsunami waves led by air pressure waves from the volcanic explosion. NOAA Center for Tsunami Research. That sentence should stop ya. Tsunami waves led by air pressure waves, not just the ocean reacting to the seafloor, not just one clean wave from one clean source. The eruption disturbed the atmosphere so violently that the sky itself became part of the tsunami story. The U.S. Geological Survey later explained that the eruption triggered two kinds of tsunamis: classic tsunamis caused by displacement of large volumes of water, and meteotsunamis caused by fast-moving pressure disturbances in the atmosphere. USGS, that is the part most people are not ready for. A tsunami warning system, at least in the public imagination, is built around earthquakes. The ground shakes, the sea reacts. The warning goes out. People move inland or uphill. That mental model saves lives when the source is a large undersea earthquake. But Hunga showed us a different door. A volcano can explode. A caldera can collapse, a flank can fail, a submarine landslide can push water, a blast wave can move through the atmosphere and press on the sea surface. And in a complex volcanic event, more than one of those mechanisms can happen at once. So when I use the phrase stealth tsunami in this script, I want to be precise. I do not mean a tsunami that no instrument can ever detect. NOAA instruments did detect Hunga. DART systems recorded it. Tide gauges recorded it. Scientists studied it. The stealth is not invisibility to science. The stealth is invisibility to ordinary expectation. This is also why language matters. Words like stealth can be useful, but only if we define them carefully. A bad definition turns the word into hype. A good definition turns it into a warning about human perception. The stealth is in the mismatch. The instrument may hear something, the ocean gauge may record something, the satellite may see something. A pressure wave may pass over weather stations. A research network may recognize an unusual pattern. But the ordinary person on the coast may still be standing inside a different story. They may be waiting for the ground to shake. They may be waiting for a volcano they can see. They may think that if there was no earthquake, there cannot be a tsunami. They may think that if the first surge is small, the danger is finished. In that moment, science can be ahead of public instinct and still not be ahead enough. A warning is not finished when it is issued. It is finished when the person at risk understands it, trusts it, and moves. That last mile is often the hardest part of any disaster system. It is also the part that rarely appears in dramatic animations. A model can show a wave crossing the Pacific, but it cannot show the father looking for a child, the hotel worker trying to tell guests to leave the beach, the harbor master deciding whether to run toward the docks or away from them, the elderly neighbor who needs help, the tourist who does not know where high ground is, or the person who loses precious minutes because the event does not look like the one they practiced. That is where a volcanic tsunami becomes more than a geologic event. It becomes a test of shared memory. The source may be hidden under the ocean, but the response has to be visible in every coastal habit: signs, drills, warnings, routes, schools, ports, hotels, and families. It is the tsunami that does not begin with the story people have rehearsed. It does not arrive after the earthquake in their mental drill. It may begin offshore underwater without strong local shaking from a volcanic source people cannot see, with mechanisms warning centers have to characterize while the water is already moving. That is the gap, and UNESCO IOC has put that gap in official language. Its volcanic tsunami monitoring guidance says recent destructive tsunamis from landslides, volcanic eruptions, and other non-seismic or complex sources show the need to improve monitoring and preparation, and that these sources make up 13% of the world's confirmed tsunamis. Tsunami Program UNESCO IOC, 13% is not the majority, but it is not zero. And when the source is close enough to people, a minority mechanism can become the only mechanism that matters. So the thesis of this episode is not that one hidden caldera is definitely about to collapse tonight. The thesis is this: the Pacific warning system is far better at recognizing the tsunami people expect than the tsunami Hunga proved is possible. And the next volcanic tsunami may not give coastal communities enough time to learn the difference. That is the real geologic disaster. Not only the eruption, the mismatch between the hazard and the rehearsal. The arc beneath the surface. To understand why this matters, we have to go under the Pacific. Not metaphorically, physically. The Tonga-Kermadec arc is part of the Pacific Ring of Fire, but that phrase has become so familiar that it almost loses meaning. People hear Ring of Fire and think volcanoes, earthquakes, red lines around an ocean basin. But a map cannot show you what the Earth is doing there. So picture the crust as two enormous sheets moving against each other. One sheet bends downward. It dives under the other. It carries oceanic crust, water-rich minerals, sediments, and stress into the deep earth. As that slab sinks, it changes. It heats, it releases fluids. Those fluids lower the melting point of the mantle above it. Magma forms. That magma rises, not in one place, in a chain. That is the arc. It is not a single volcano. It is a whole conveyor of volcanic possibility. Some centers rise above the ocean as islands. Many do not. Many remain submerged, their summits hidden underwater, their slopes shaped by eruptions, collapses, landslides, vents, and hydrothermal circulation. GNS Science describes the Kermadec arc as extending more than 1,200 kilometers northeast, as mainly submarine volcanic centers lying on or near the Kermadec Ridge. The broader Tonga-Kermadec system is one of the most active submarine volcanic regions on the planet. GNS Science? That scale matters. Because most people are used to thinking about volcanoes as landmarks. Mount St. Helens, Krakatoa, Etna, Fuji, Vesuvius. Names tied to places you can picture. Submarine volcanoes break that habit. They are not landmarks for the public. They are features in bathymetric surveys, acoustic records, plume detections, satellite anomalies, and research expeditions. A fishing vessel can pass over one and see nothing. A satellite can photograph the ocean above it and see only blue. A coastal community can live within range of its consequences without knowing its shape. A land volcano is a building with smoke coming out of it. A submarine volcano is a machine in the basement of a flooded house. You may know the house exists. You may know the basement is there. But unless you have mapped the room, installed sensors, and kept listening, you do not know which pipe is shaking. That is the monitoring problem. And this is where I want to be very careful. Scientists are not blind. The ocean is not unstudied. The Tonga-Kermadec system has been surveyed by research vessels. Volcanoes like Brothers, Monowai, Havre, and Hunga have been studied in detail at different times. NOAA, GNS Science, universities, and international teams have mapped, sampled, and monitored pieces of this arc. But pieces are not the whole. The ocean is enormous. Ship time is expensive. Repeat surveys are limited. Instruments are sparse compared with the scale of the hazard. A volcano can change between mapping campaigns. A flank can weaken quietly. A vent field can migrate. A crater can deepen. A new cone can form. A hydrothermal system can intensify. The seafloor does not send daily status updates unless someone has built the system to hear them. That is why the phrase unmapped volcano is both powerful and dangerous. It is powerful because parts of the seafloor really are less well known than many people assume. It is dangerous because it can make the public think scientists know nothing. The truth lives between those extremes. We know enough to understand the hazard class. We do not know enough to watch every source continuously. And in a volcanic tsunami, that difference can be measured in minutes. Why Hunga changed the question before Hunga, volcanic tsunamis were not a mystery. Krakatoa in 1883 produced one of history's most infamous volcanic tsunamis. Anak Krakatoa generated a deadly tsunami in 2018 after flank collapse. Submarine eruptions, caldera collapses, pyroclastic flows entering water, and volcanic landslides have all been recognized tsunami sources. So Hunga did not reveal a brand new category. It did something more useful. It reminded the modern warning system that the category is not theoretical. On January 15, 2022, Hunga produced a tsunami that reached Tonga and traveled across the Pacific. NOAA recorded the event through DART systems and sea level gauges. USGs describe both classic tsunami waves and meteotsunamis generated by atmospheric pressure disturbances. NOAA Center for Tsunami Research, that is already enough to matter. But the real shock was the complexity. A typical earthquake tsunami begins with seafloor displacement. The earthquake lifts or drops part of the seabed, the ocean surface is disturbed, and waves radiate outward. There are complexities, but the basic mechanism is direct. Hunga was not that simple. The eruption displaced water, yes, but it also launched atmospheric waves. Those waves moved rapidly around the planet. They pressed on the ocean surface. They created meteotsunami signals in places where a classic tsunami travel time estimate did not fully explain the timing. Imagine the ocean as a long rug. An earthquake tsunami is like lifting part of the rug from underneath and letting the ripple run outward. Hunga also slapped the rug from above. That is why scientists had to untangle the wave record. The DART bottom pressure recorders were seeing tsunami waves led by air pressure waves. The data were valuable, but the mixture complicated source analysis and modeling. NOAA Center for Tsunami Research. This is what people often miss about modern monitoring. Detection is not the same as immediate understanding. A useful way to think about this is the difference between hearing a crash in another room and knowing what broke. The sound tells you something happened. It does not tell you whether a glass fell, a shelf collapsed, a window shattered, or a wall gave way. Your response may need to begin before you have inspected the room. Warning centers face a version of that problem, except the room is an ocean basin. They may see pressure data, seismic data, sea level data, satellite observations, and reports from people near the source. Each stream carries information, but not all of it arrives at the same speed or with the same certainty. A pressure signal can be fast. A tide gauge can confirm water movement at a specific place. A dark buoy can show a passing wave. A satellite image can reveal a plume or discoloration, but not necessarily in the first minute. Bathymetric change may not be known until later. Eyewitness reports can be crucial, but they can also be delayed, incomplete, or disrupted by the disaster itself. The decision problem is merciless because waiting for perfect certainty can cost lives, while warning too broadly can create confusion and fatigue. This is not a simple problem of courage. It is a problem of thresholds. How much evidence is enough to issue an advisory? How much uncertainty should be included in the message? How do you warn about a complex source without burying the public in complexity? How do you say, we do not yet know the full mechanism, but you still need to leave the coast now? Those questions are not abstract. They define the minutes between detection and movement. And because volcanic tsunamis can involve more than one mechanism, the message has to be designed for uncertainty. It cannot depend on explaining every detail in real time. It has to teach people in advance that the ocean can become dangerous even when the usual earthquake cue is absent. A sensor can tell you something happened. A buoy can record a wave. A pressure gauge can capture a signal. A satellite can see a plume. But the warning problem is not just did something occur. The warning problem is what occurred, how much water moved, which coasts are at risk, how fast will the waves arrive, how large might they be, is the first wave the largest, is the source still active, and are more waves coming? That is a lot to answer while the clock is running. Hunga forced those questions into the open, and the official response after Hunga did not say, everything is fine. UNESCO IOC's guidance on volcanic tsunamis exists because these complex sources need better monitoring, clearer institutional roles, and standard operating procedures that connect volcano observatories with tsunami warning centers. Tsunami Program UNESCO IOC, translated out of institutional language, that means the earthquake playbook is not enough. That is the heart of this story. The first warning may be the sea itself. The most terrifying warning is the one that arrives before the alert. A strange withdrawal of water. A sudden surge, a harbor current that should not be there. A boom from offshore, a pressure wave nobody understands in the moment. A message that reaches one island, but not another. A wave that arrives before the public has a name for what happened. That is the near-source tsunami problem. For far-field coastlines, there may be time. Dark buoys can detect. Warning centers can model. Alerts can propagate. People may have hours. But for communities close to a volcanic source, the first minutes are everything. And volcanic sources can be messy. They may not provide the clean earthquake trigger that activates public intuition. They may not shake a coast hard enough to make everyone run. They may be hidden by water. They may be surrounded by islands where people know the sea, but not the deep structure beneath it. They may produce a sequence of waves where the first arrival is not the largest. That last point matters. One of the most dangerous tsunami behaviors is false reassurance. The first wave comes in. It looks manageable. People return. They film. They check boats. Then a later wave or surge arrives larger, stronger, longer, and full of debris. Tsunamis are not normal waves. They are moving water columns. The danger is not just height. It is speed, it is current, it is duration, it is debris. It is the way water fills a harbor, reverses direction, tears boats loose, lifts cars, and turns familiar coastlines into moving machinery. A 1-meter tsunami can be deadly in a harbor. A 2-meter surge can destroy. A wave does not need to look like a Hollywood wall to kill you. That is why natural warning education remains essential. If the ocean suddenly withdraws, move. If the sea behaves strangely, move. If an official alert tells you to evacuate, move. If you are near a coast and feel long or strong shaking, move. And for volcanic regions, if there is an eruption, explosion, ashfall, unusual water behavior, or official warning, do not wait to understand the entire mechanism. Move first, understand later. That is a hard message for modern people because we are used to explanation before action. We want confirmation, we want maps, we want arrival times. We want someone with authority to tell us whether the danger is real. But water does not wait for certainty. And in the closest communities, certainty may arrive after the wave. That is what not ready means. Not that nobody has a warning center. Not that nobody has instruments. Not that scientists are asleep. It means the public mental model is still too earthquake-centered for a hazard that may not begin with an earthquake. It means the monitoring is improving, but uneven. It means the chain between volcanic unrest, ocean response, warning decision, local communication, and human movement still has weak links. And in a tsunami, one weak link can be enough. The real premise, so let me restate the episode in the cleanest way. This is not a confirmed emergency bulletin about one newly awakening caldera. This is an investigation into a real hazard exposed by a real eruption in a real volcanic arc. The Tonga-Kermadec system contains dozens of submarine volcanoes. Hunga proved that a volcanic eruption can generate a complex tsunami that does not behave like the standard earthquake-only scenario. NOAA detected the event, but the mixed air pressure and tsunami signals complicated interpretation. USGS documented both classic tsunamis and meteotsunamis. UNESCO IOC now says volcanic and other non-seismic tsunami sources require better monitoring, warning procedures, and preparedness. GNS science, that is the story, and it is enough.
Because the next dangerous volcanic tsunami does not need to be global to be catastrophic. It only needs to be close. Close to a low island, close to a harbor, close to a fishing community, close to a tourist beach, close to a coastline where people are waiting for earthquake shaking that never comes. That is the disaster that can unfold overnight. Not because the Earth is trying to surprise us, because the Earth does not care which warning signs we prefer.
The caldera collapse problem. A caldera is not a crater in the simple way most people imagine it. A crater is often a hole blasted or built at the surface. A caldera is a failure structure. It forms when the ground above a magma system loses support and collapses. Sometimes that happens after magma drains away, sometimes during a major eruption. Sometimes as part of a complicated sequence of explosion, evacuation, cracking, and subsidence. Picture a cake sitting on a table. Now imagine someone scoops out the middle from underneath. The top may look stable for a moment. Then cracks appear. The surface sags. A section gives way. The whole center drops. That is the caldera idea. Now put that cake under the ocean. Everything changes. The underwater version also adds a psychological trap. When people hear the word collapse, they may imagine one clean drop, one clean splash, one clean wave. Real volcanic structures can fail in messier ways. A section may slump, a wall may fracture, material may slide in pulses, an eruption may remove support while explosions continue. A crater may deepen, widen, or reorganize. The source may not behave like a single switch that flips from stable to failed. That matters for how waves are generated. A fast, coherent displacement can be more efficient at moving water than a slower, drawn-out deformation. A landslide aimed toward one direction can focus energy unevenly. A shallow event may couple to the ocean differently than a deep one. A source close to land may cause severe local effects, even if the signal is not dramatic across the whole ocean. This is why the careful version of the claim is stronger than the sensational version. The sensational version says, caldera collapse equals mega tsunami. The careful version says, rapid displacement at or near a submarine volcanic system can generate dangerous waves, and the danger depends on geometry, speed, volume, depth, and distance to people. That may sound less explosive, but it gives emergency managers something to work with. It also avoids a mistake that weakens public trust. If every volcanic collapse is described as apocalyptic, then the public learns to ignore the language. If every underwater eruption is framed as a basin-wide catastrophe, then smaller but deadly local hazards may be misunderstood. The truth is more variable and more useful. A volcanic tsunami can be local, regional, or far-field. It can be devastating in one harbor and modest elsewhere. It can be deadly because of currents rather than towering height. It can be dangerous long after the first arrival. Precision is not the enemy of urgency. Precision is how urgency survives scrutiny. Because when rock drops underwater, water has to move. When a volcanic wall fails, water has to move. When a flank slides, water has to move. And when water is displaced quickly, the ocean tries to restore itself. That restoration becomes a wave. This is the simplest tsunami mechanism in the world. Push water out of place, and gravity pulls it back. But the details decide whether the result is nothing, a local hazard, a regional disaster, or an ocean-wide warning. How much material moved? How fast? In what direction? At what depth? Did the collapse happen vertically, laterally, or as a landslide? Was the eruption still ongoing? Did an atmospheric pressure wave add energy? Did the source sit close to populated coastlines? Those are not academic questions. Those are the difference between a geological event and a human disaster. The original pitch for this episode says that if the rim of an underwater caldera collapses, it will instantly displace billions of tons of water and generate a massive high-velocity stealth tsunami. That is physically imaginable in a broad sense, but it is too certain as written. Not every caldera collapse creates a catastrophic tsunami. Not every submarine eruption collapses. Not every collapse moves enough water fast enough. Not every tsunami travels as a devastating basin-wide wave. The water depth, geometry, volume, collapse rate, eruption style, and distance to shore all matter. So the accurate version is this. A sudden collapse, landslide, or explosive displacement at a submarine volcanic system can generate a tsunami without the classic earthquake warning sign. And if that source is close to people, the warning window can be brutally short. That is the danger. Not the word caldera, the displacement. And Hunga makes this discussion real because Hunga itself was part of a largely submarine volcanic system. Smithsonian's Global Volcanism Program classifies Hunga Tonga Hunga Ha'apai as a caldera volcano with its last eruption in 2022. The Tonga-Kermadec volcanic region also includes active or recently active systems such as Home Reef and Tofua, with the Global Volcanism Program listing current continuing activity in the region as of March 31, 2026. Smithsonian Global Volcanism, that does not mean any one of those volcanoes is about to produce a Hunga-scale tsunami. It means the region is alive enough that volcanic tsunami readiness cannot be treated as a historical curiosity. This is what I find so important. The hazard is rare, but the source region is not dormant. Rare event, active region, limited public mental model. That is the combination. Why underwater eruptions are not simple. A land eruption gives you evidence your eyes can understand. A plume, ash, lava, glow, pyroclastic flows, evacuation maps, a volcano observatory bulletin. A submarine eruption may give you signs that are stranger and more indirect. Discolored water, floating pumice, gas bubbles, a strange acoustic signal, a new island that appears and then erodes away, a pressure wave, a satellite anomaly, a tsunami record. And sometimes, if the eruption is deep enough, the ocean may hide much of the surface drama. The ocean is a blanket. Sometimes it muffles the eruption. Sometimes it hides the eruption. Sometimes it becomes part of the eruption. That last one depends on physics. Very hot magma meeting water can produce explosive water-magma interaction. Water flashes into steam. Magma fragments. Energy is transferred violently. In shallow marine settings, this can produce Surtzian eruptions, ash, steam blasts, and the building of temporary islands. But depth matters. Pressure matters. Deep water can suppress steam expansion. A deep submarine eruption may behave very differently from a shallow one. So it is not correct to say that deep-sea eruptions are infinitely more dangerous because they meet cold seawater. That phrase sounds dramatic, but it is not how the hazard works. The accurate statement is more interesting. Submarine eruptions are harder to interpret because the ocean changes both the eruption and the evidence. At some depths, water suppresses explosions. At other depths and vent conditions, water intensifies fragmentation. At some volcanoes, the eruption stays mostly local. At others, collapse or landslide can displace water. In extreme explosive events, the atmosphere itself can become part of the tsunami generation system. That is the Hunga lesson. NOAA's records show that dark bottom pressure recorders captured waves of the Tonga tsunami led by air pressure waves from the volcanic explosion, and that the mixture of signals complicated the tsunami analysis and source inversion process. NOAA Center for Tsunami Research. That means the instrument network was not useless. It was seeing something. But what it was seeing did not fit the simple version of the playbook. This is where the phrase warning system has to be understood as more than sirens. A warning system is a chain of interpretation. Sensor detects, data transmits, analyst or algorithm identifies. Model estimates, center issues. Government relays, community receives, person believes, person moves, every link matters. The chain also has a human weak point that no sensor can fully remove, belief. People are more likely to act when a message feels consistent with what they already know. That is why earthquake education has been powerful. Long or strong shaking near the coast is simple. It is physical. It does not require a phone signal. It gives the body a reason to move. But a volcanic tsunami warning may ask people to act without that bodily proof. It may ask them to leave a beach under a blue sky. It may ask them to abandon a harbor because of an eruption they did not see. It may ask them to trust that a distant or underwater event has made the sea dangerous, even while the coastline still looks calm. That is a different kind of trust. Trust is built before the alert. It is built when schools practice. It is built when hotel staff know the route. It is built when signs explain that tsunamis can be generated by earthquakes, landslides, eruptions, and unusual sea behavior. It is built when local leaders repeat the same message until it becomes boring. Boring is good. Boring means the message is familiar enough to survive fear. In disasters, familiarity is speed. A person who has never imagined a volcanic tsunami may spend the first minute arguing with the warning. A person who has practiced the idea may already be walking uphill. That difference may be the entire margin. So when we talk about warning chains, we should not picture only instruments and agencies. We should picture the chain ending inside a person's decision. The last link is not a buoy. It is a human being choosing to move before curiosity, skepticism, or social pressure keeps them near the water. And volcanic tsunamis stress the early links because the source can be ambiguous. Was there a collapse? Was there an explosion? Was the sea surface pushed by an atmospheric wave? Is this a local water displacement wave, a basin-wide meteotsunami, or both? Are additional waves coming? Did part of the volcano fail? Is the eruption continuing? A tsunami warning center may need to decide before all those answers are known. That is a brutal position, and it is why post-Hunga work matters so much. The goal is not to say the system failed and leave it there. That would be unfair. The system detected Hunga. Alerts were issued. Scientific networks recorded an extraordinary event. People survived because of warning, natural cues, and community response. The better question is, what did the system have to learn in real time? Because that is where the next improvement lives. What the sensors can see the ocean is not unmonitored. I want to make that clear because the disaster movie version of this story often depends on pretending the Pacific is just empty water. It is not. There are dart buoys, tide gauges, seismic stations, hydrophones, satellites, research vessels, autonomous platforms, volcano observatories, regional tsunami warning centers, local emergency agencies, scientific networks that spend their lives listening to signals most of us never think about. During Hunga, NOAA says the tsunami was detected by virtually all available DART systems and the majority of coastal sea level gauges around the United States and the Pacific. NOAA Center for Tsunami Research. That is extraordinary, and it matters. But a DART buoy is like a smoke detector in a warehouse. It can save lives. It cannot see every room. A DART system records changes in bottom pressure caused by passing tsunami waves. That tells warning centers that a wave exists and helps constrain its behavior. But detecting the wave after it is generated is not the same as fully understanding the source while it is forming. To understand a submarine volcanic source, you need a different kind of picture. You need bathymetry, which is the shape of the seafloor. Think of bathymetry as the face of the underwater mountain. Is there a crater, a caldera, a steep flank, a scar from a landslide, a new cone, a dome, a channel that could direct a collapse? You need repeat bathymetry because one map is only one moment. A volcano can change, a vent can build, a crater can deepen, a flank can fail. You need hydroacoustic monitoring because water carries sound efficiently. Eruptions, landslides, cracking, and explosions can produce acoustic signatures. You need water column chemistry because hydrothermal systems release heat and chemicals that can signal activity. You need satellite observations when the eruption reaches or affects the surface. You need local reports because fishermen, island residents, and mariners sometimes see the first surface clue. And then you need all of that to connect quickly enough to a warning decision. That is the hard part. Data are not the same as readiness. A pile of instruments does not automatically produce a clear public message. Someone has to know what the signals mean. Someone has to decide the threshold for action. Someone has to translate uncertainty into instructions. That is where UNESCO IOC's volcanic tsunami guidance becomes important. It recommends better coordination among tsunami warning centers, volcano service providers, and national authorities because volcanic tsunami sources do not fit cleanly into earthquake-only workflows. Tsunami Program UNESCO IOC, that is not glamorous. It is not a viral headline, but it is the difference between a strange signal and a useful warning. The stealth tsunami mechanism. Let's build the stealth tsunami from the ground up. First, something happens at the volcano. It could be an explosive eruption. It could be a collapse. It could be a flank landslide. It could be pyroclastic material rushing into water. It could be a pressure wave from a large blast. In the most complex events, it could be several of those mechanisms together. Second, water is forced out of place. That might happen directly as rock or eruptive material pushes water aside. It might happen because the seafloor drops and the water column responds. It might happen because an atmospheric pressure wave presses on the sea surface and transfers energy into long waves. Third, the wave spreads. In deep ocean, a tsunami may have a small wave height but an enormous wavelength. A ship at sea may barely notice it. The surface may not look dramatic, but the energy is distributed through a huge moving water column. Fourth, the wave reaches shallow water. Now the ocean floor rises under it. The wave slows. The energy compresses. The water piles upward and pushes inland into harbors, bays, reefs, river mouths, and coastal plains. That is when the harmless-looking open ocean wave becomes a coastal event. The stealth problem enters at step 1. If the source is an earthquake, the warning chain has a familiar beginning. Seismic networks detect the earthquake. Magnitude, depth, location, and focal mechanism give clues about tsunami potential. If the source is volcanic, the beginning is less clean. There may be seismicity, but not the right kind. There may be an explosion, but the relationship between explosion size and tsunami size may be uncertain. There may be a collapse that is not immediately mapped. There may be a pressure wave moving faster than the classic tsunami arrival time. Yuskis says the Hunga eruption generated classic tsunamis from water displacement and meteotsunamis from atmospheric pressure disturbances. It also says some first arriving waves in Japan came more than 2 hours earlier than expected for a classic tsunami from Tonga because they were pushed by atmospheric pressure waves moving at roughly 700 miles per hour.
Oof.
That is the source of the unease. The ocean can respond before your simple model says it should, and the public does not live inside the technical model. Most people do not know the difference between a classic tsunami and a Mititu tsunami. They do not know what a lam wave is. They do not know what a dart bottom pressure recorder is seeing. They know whether their phone screamed, whether the siren sounded, whether the sea looks wrong, and whether someone they trust told them to move. That is why communication matters so much. A stealth tsunami is not just a physical hazard. It is a messaging hazard. If the alert says tsunami but the person did not feel an earthquake, will they believe it? If the first wave is small, will they return? If the water pulls back, will they go look? If the source is a volcano they cannot see, will they understand why the ocean is dangerous? Those are life and death questions, and they have to be answered before the event, not during it. The Hunga sequence Hunga was terrifying because it made the hidden visible. A mostly submarine volcano in the Tonga region erupted with enough violence to send a plume into the upper atmosphere, generate tsunami waves, and create a global pressure signal. NASA's Earth data describes the 2022 eruption as a major data case for studying the tsunami generated by Hunga, including model simulations and satellite sea surface height observations. NASA Earth data. The eruption did not stay local in the scientific record. It appeared in barometers, in ocean gauges, in satellite data, in DART records, in field surveys, in damaged coastlines. That is what a compound geophysical event looks like. It crosses categories: volcano, ocean, atmosphere, coast, infrastructure, emergency management, public trust. And yet, the human experience was still immediate. People in Tonga did not experience an academic category. They experienced ash, noise, darkness, water, damage, isolation, and uncertainty. Communications were disrupted. The eruption severed undersea cable connections. Ashfall affected water supplies. The tsunami destroyed homes and coastal infrastructure. That is the part that cannot get lost in mechanism. A warning system is not built to satisfy scientists. It is built so families move before water arrives. And Hunga's relatively limited death toll compared with the scale of the physical event should not make anyone complacent. It should make us ask what went right and what depended on luck.
Some communities had natural warning. Some had enough elevation nearby. Some had prior tsunami education. Some had time. Some had people who understood that the first wave might not be the last. But another eruption in another place at another hour near another coastline may not give the same sequence. That is the concern. Rare does not mean one-off. It means the next version may arrive before the world has practiced enough.
The map is not the hazard a tsunami map can make danger look clean. Colored zones, arrival time lines, wave height estimates, dots for tide gauges, triangles for dart buoys. A neat ocean basin reduced to curves and labels. But the map is not the hazard. The map is a translation of the hazard, and volcanic tsunamis are hard to translate quickly. At Hunga, the ocean and atmosphere were both involved. NOAA's DART systems recorded tsunami waves led by air pressure waves, and USGs later described the event as producing both classic tsunamis and meteor tsunamis. NOAA Center for Tsunami Research. That means the first map may not capture the whole behavior. The first arrival may not be the most damaging. The first mechanism may not be the only mechanism. The first public explanation may be incomplete because the event itself is still unfolding. That is normal in science, but it is difficult in emergencies. People do not respond well to changing messages. They want one answer: evacuate or do not evacuate, safe or unsafe, big or small, local or basin-wide. The ocean does not always give answers in that format. A volcanic tsunami might produce strong currents in one harbor, inundation on one island, strange early waves far away, and later surges that are more dangerous than the first arrivals. A pressure wave might create sea-level disturbances that confuse expected timing. A collapse or landslide might send energy directionally, hitting one coastline much harder than another. This is why the phrase tsunami height can mislead. People hear height and imagine a wall. But a tsunami's danger is not only height. It is the whole movement of water. A long surge can push inland and stay. A harbor oscillation can last for hours. Currents can reverse and strengthen. Debris can turn the water into a battering ram. A wave that looks unimpressive from a safe distance can be lethal up close. This is especially true in harbors. Boats break loose, lines snap, docks fail. People standing near the water get swept. The event can continue long after the first arrival. The all clear matters. That is a warning communication problem, because a person who sees a small first wave may decide the alert was exaggerated. And if the larger surge comes later, that false lesson can kill. So the public message has to be repetitive and blunt. The first wave may not be the largest. Stay away from the coast until officials give the all clear. Do not go to the shore to watch. Move inland or uphill immediately when told. If the sea behaves strangely, leave. These messages are simple because the moment is not. In a volcanic tsunami, complexity belongs behind the scenes. The public instruction has to be clean, but clean does not mean incomplete. People also need to know that not all tsunamis start with an earthquake. That one sentence may be the difference between belief and hesitation. Not all tsunamis start with an earthquake. That belongs on signs, drills, schools, tourism materials, harbor briefings, and emergency alerts in volcanic regions. Because the wrong expectation can delay the right action. Why the Pacific is exposed. The Pacific is not one coastline. It is thousands of coastal lives wrapped around one ocean. Island nations, atolls, fishing villages, ports, military bases, tourist beaches, resorts, schools, hospitals, fuel depots, coastal roads, low-lying neighborhoods, indigenous communities, places with sirens and evacuation maps. Places where the warning chain still depends on radios, churches, phones, families, and someone driving through town telling people to move. The hazard is shared, the capacity is not. That is one of the uncomfortable truths about tsunami readiness. A warning center can issue a technically correct message. The message can still fail locally. Maybe the signal does not reach people. Maybe it reaches them in a language they do not understand. Maybe people do not trust the authority sending it. Maybe tourists ignore it because they think tsunami warnings only follow earthquakes. Maybe older residents cannot move quickly. Maybe roads are blocked. Maybe the event happens at night. Maybe the eruption also disrupts communications. Preparedness is not a document. Preparedness is choreography. Who hears the alert? Who translates it? Who checks on the elderly? Who opens the evacuation center? Which road goes uphill? Which route floods first? Who has the key? Who has the radio? Who decides the all clear? That choreography has to exist before the eruption because during the event there is no time to invent it. That choreography should include the uncomfortable details. Where do people go if the main road is already crowded? What happens if the power fails? Who checks the beach at night? How are visitors warned when they do not speak the local language? What does the harbor do with boats already in the water? Who has authority to close the waterfront? How does a school move children quickly without waiting for every parent to arrive? What happens if ash fall, heavy rain, or damaged communications occur at the same time? Compound hazards create compound confusion. Hunga was not only a tsunami event. It involved ash, communication disruption, infrastructure damage, and uncertainty. That kind of layering is what makes volcanic events especially difficult. A community may be dealing with air quality, water supply, darkness, damaged roads, and a tsunami threat at the same time. Preparedness has to admit that reality. A clean drill is better than no drill, but a mature drill asks what happens when the clean version fails. It asks whether people can evacuate in the dark, whether the route is obvious without signs, whether a siren is enough for people indoors, whether the evacuation site has water, whether people with disabilities have help, whether families know not to drive toward the school if the safer action is for the children to move with teachers. None of this is glamorous. It will not trend the way an eruption satellite image trends. But it is the part that decides outcomes. A community does not rise to the drama of a disaster. It falls back on what it has practiced. If the only practice story is earthquake, shaking, siren, evacuation, then a volcanic tsunami begins with a disadvantage. The practice has to be wider than the most familiar trigger. UNESCO IOC's volcanic tsunami guidance recognizes this at the system level. It calls for designated organizations, monitoring instrumentation, standard operating procedures, and cooperation among tsunami warning centers, volcano service providers, and national authorities. Tsunami Program UNESCO IOC. That sounds bureaucratic, but it is survival language. It means someone has to own the volcanic tsunami problem, not in theory, operationally. Because if the source is volcanic, the first agency to know something is wrong may not be the same agency that issues tsunami warnings. A volcano observatory may see unrest. A tsunami center may see a sea level anomaly. A meteorological network may record pressure waves. A local community may see unusual water before the official chain has a complete picture. All of those signals have to meet, fast. That is the difference between a warning system and a collection of instruments. A warning system is connected. A collection of instruments is just evidence waiting to be interpreted, and the Pacific has too many vulnerable places to rely on disconnected evidence. This is especially true for low-lying islands. There may be no high mountain nearby. Evacuation may mean reaching a designated structure, a small rise, or a limited inland zone. Roads may be narrow. Vehicles may be scarce. Nighttime evacuation may be difficult. A warning with 5 hours is one problem. A warning with 15 minutes is another. That is why near-source volcanic tsunamis are so frightening. They compress everything: detection, decision, communication, movement, all into a window that may be shorter than one news broadcast. The disaster movie version now. I want to take the disaster movie version of this story head on. The claim goes like this. A secret, unmapped submarine mega caldera is waking up. Sensors know it. Officials are not ready, and a massive stealth tsunami could cross the Pacific without warning. That version is not supported by the evidence. I cannot verify the secret awakening caldera claim. I cannot verify that an official sensor network is currently detecting a specific massive caldera on the edge of collapse. And I cannot responsibly tell you a basin-wide tsunami is about to happen overnight. That matters. Because when we inflate a real hazard with unsupported details, we make the real hazard easier to dismiss. Someone hears the exaggerated version, finds out part of it was wrong, and then decides the whole topic is fake. That is how bad communication harms preparedness. So let's separate the real from the invented. Real. The Tonga-Kermadec arc contains many submarine volcanoes and active hydrothermal systems. GNS Science Real. Hunga generated a complex tsunami involving water displacement and atmospheric pressure waves. Real. NOAA's DART systems recorded the tsunami and pressure wave-led signals. NOAA Center for Tsunami Research Real. UNESCO IOC says volcanic and other non-seismic tsunami sources require improved monitoring and warning procedures. Tsunami Program UNESCO IOC, not verified, that a newly discovered unmapped caldera is confirmed to be awakening right now. Not supported. That deep-sea eruptions are always more dangerous than land eruptions. Not responsible, saying a stealth tsunami would cross the Pacific with no warning at all. The warning gap is real. The certainty is not, and that distinction is the whole reason to trust the script. Because the real story is not weaker than the fake version. It is stronger. The fake version depends on a secret. The real version depends on a documented failure mode. Hunga already happened. The instruments already recorded the unusual signal. Scientists already published the mechanisms. UNESCO IOC already produced guidance. The arc already contains submarine volcanoes. We do not need a fictional caldera to make the risk worth taking seriously. The honest Steelman, but I also want to be fair to the fear behind the exaggerated claim. People are not irrational for worrying about submarine volcanoes. They remember Hunga. They saw satellite images of a plume exploding into the atmosphere. They heard that the pressure wave went around the world. They heard that the eruption generated tsunami waves across the Pacific. They understand at a gut level that a volcano under the ocean is harder to watch than one on land. That instinct is not wrong. It just needs better structure. The honest version is this: the Pacific has active submarine volcanic arcs. Some of those volcanoes are incompletely monitored. Some eruption mechanisms can generate tsunamis without a large tectonic earthquake. Existing tsunami warning systems are strong, but their public mental model and operational workflows have historically centered on seismic sources. Hunga proved that volcanic tsunamis can be compound events involving ocean displacement and atmospheric forcing. Therefore, the system needs better volcanic tsunami monitoring, clearer warning procedures, and better public education. That is the Steelman. No conspiracy, no secret countdown, no guarantee. Just a real hazard class and a real readiness gap. This Steelman also helps the audience avoid two bad reactions. The first bad reaction is panic, believing every underwater signal means catastrophe, treating every new island or pumice raft as a countdown, and sharing warnings that have no official basis. Panic burns trust quickly. It can send people toward bad information and make them less responsive when a real alert arrives. The second bad reaction is dismissal, deciding that because one dramatic claim was exaggerated, the entire category is fake. Dismissal is just as dangerous. It leaves the old mental model untouched. It tells people they only need to worry about the earthquake version. It turns Hunga into an oddity instead of a lesson. The right reaction is disciplined attention. Disciplined attention means asking better questions. What is the source? Which agency confirmed it? Is there sea level evidence? Is there a tsunami bulletin? Are local authorities changing guidance? Is the report describing normal volcanic activity, an eruption, a collapse, or only speculation? Does the claim distinguish between a local hazard and a basin-wide hazard? Does it explain uncertainty honestly? These questions protect people from hype without making them complacent. They also make the story more credible. A documentary script does not become stronger by pretending uncertainty does not exist. It becomes stronger by showing the audience which uncertainties matter. We do not know when the next dangerous volcanic tsunami will occur. We do know that volcanic tsunamis exist. We do know that some sources are close to vulnerable coastlines. We do know that public expectations can lag behind hazard science. We do know that preparedness can reduce that gap. That is enough to justify attention. And if I were writing the hook for this episode, that is where I would aim. Not they are hiding a mega caldera. That is cheap. The better hook is, the next tsunami may not start with the warning sign you were taught to wait for. That is true. That is frightening. And that is useful. What would actually make this urgent? So what would move this story from background hazard to immediate breaking event? Not a viral post. Not a scary map. Not one anonymous claim. Signals. First, confirmed eruptive activity from a known submarine or island volcano near a vulnerable coastline. Second, a sustained swarm of volcanic earthquakes or hydroacoustic signals consistent with unrest at a specific volcanic center. Third, satellite evidence of a plume, thermal anomaly, new island growth, discolored water, or pumice raft. Fourth, tide gauge or dart anomalies following an eruption signal. Fifth, official bulletins from recognized agencies. Tonga Geological Services, GNS Science, NOAA, the Pacific Tsunami Warning Center, National Emergency Agencies, or Smithsonian's Global Volcanism Program. Sixth, credible reports of collapse, flank failure, or rapid bathymetric change. Seventh, any tsunami information statement, advisory, watch, or warning. That is the escalation ladder. And notice what is not on it. A single dramatic model image, a social media thread, a caption saying scientists are baffled, a video claiming the government is hiding a wave. Those are not escalation. They are noise. The atmosphere, ocean, and solid earth all produce enough danger without us adding noise. The real work is knowing which signals matter. For a submarine volcanic tsunami, the most important signals are multi-system. You want volcanic monitoring, ocean pressure data, sea level gauges, satellite observations, acoustic signals, and official analysis converging on the same concern. One signal can be ambiguous. Several independent signals can become a warning. That is how this should be handled. Not with panic, with convergence. The local disaster scenario, the most concerning version of this hazard, is not necessarily an ocean-wide apocalypse. It is a local disaster with almost no time. A submarine volcano erupts or collapses near an island chain. The source is close, the wave is generated quickly. The first official interpretation is uncertain because the trigger is not a large earthquake. The community does not feel strong shaking. Some people hear a boom, but others do not. The sea begins to behave strangely. A tide gauge shows a signal. A warning center is still trying to determine whether the event is local, regional, or broader. The first wave reaches low-lying areas before the public fully understands what happened. That is the nightmare. Not because the wave crosses an entire ocean invisibly, because the closest people have the least time. Distance is warning. Near-source communities do not have much distance. That is why natural cues matter so much. Strange sea behavior is not a curiosity. It is an instruction. A sudden withdrawal, surge, roar, or unusual current near a volcanic region should not be filmed from the shore. It should trigger movement. Move inland. Move uphill. Do not wait. The problem is that this message has to compete with human curiosity. People walk toward danger when it looks strange. They film. They gather. They assume the official alert will come before the real hazard. But in a near-source tsunami, the ocean may be faster than the message. That is the readiness gap in its most human form. Not enough practice. Not enough instinct. Not enough trust in natural warning signs. And maybe not enough time. Now imagine that same scenario from the point of view of one coastal town. It is late. The water is dark. The first clue is not a siren, but a message passed from person to person. Something happened offshore. Some residents hear a distant boom. Others hear nothing. A few phones receive an alert, but the wording is cautious because the source is still being assessed. At the harbor, the water begins to pull in an odd direction. A boat strains against its lines. Someone walks closer to film it. Someone else remembers the drill and starts shouting for people to leave. This is where readiness either becomes real or collapses into argument. One person says there was no earthquake. Another says the alert might be a false alarm. Another says they need to check the boat. A parent tries to call a child. A visitor asks where the evacuation route is. A shop owner wants to lock the door. The first minutes disappear into ordinary human impulses, most of them understandable. Disasters exploit understandable behavior.
People want information. They want property protected. They want family together. They want proof. They want to see the thing before they believe it. But the safest tsunami response often asks them to do the opposite. Leave before proof. Abandon property. Move before the family is perfectly assembled. Trust the route and accept that the water may become deadly before the explanation becomes complete. That is why coastal culture matters. In a prepared community, the person shouting leave is not treated as dramatic. They are recognized as repeating the rule. In an unprepared community, that same person may be ignored until the sea makes the argument for them. By then, the town may have lost the only minutes it had.
Interpretation 1, the reassuring version. The most reassuring interpretation is that this remains a background volcanic hazard, not an immediate crisis. In this version, the Tonga-Kermadec arc is active because it is always active in a geological sense. Submarine volcanoes vent heat. Hydrothermal systems pulse. Small eruptions occur. Temporary islands form and erode. Pumice rafts drift. Scientists monitor, map, and update databases. But none of that means a major tsunami-producing collapse is imminent. This interpretation deserves real weight. A careful person does not turn every active volcanic arc into a countdown. Most submarine volcanic activity does not produce a catastrophic tsunami. Many eruptions remain local. Some are suppressed by pressure, some build seafloor features without major water displacement. Some produce surface discoloration or pumice, not disaster. Even Home Reef, which has had recent activity and island building behavior in Tonga, is described by NASA Earth Observatory as much tamer than Hunga, with officials saying it poses low risk to nearby inhabited islands. NASA science, that is important, because the existence of activity is not the same as the existence of emergency. The reassuring interpretation says, yes, the region is active. Yes, volcanic tsunamis are real. Yes, monitoring should improve. But no, there is no verified evidence that a catastrophic event is imminent tonight. That may be the most likely day-to-day reality. And if that is true, the response should be steady investment, not panic. More mapping, better sensors, better coordination, better public education, more drills, better local evacuation routes. This is the slow work, the unglamorous work, the kind that saves lives before anyone is watching. Interpretation 2. The evidence weight concern. The middle interpretation is the one the evidence most strongly supports. The Pacific is not facing a confirmed overnight volcanic disaster, but it is facing a real preparedness gap for volcanic and other non-seismic tsunamis. This is where I land. Hunga showed the problem. NOAA recorded complex signals. ESGs documented both classic tsunamis and medio tsunamis. UNESCO IOC said volcanic, landslide, and other complex tsunami sources make up a meaningful share of confirmed tsunamis and require better monitoring and warning preparation. NOAA Center for Tsunami Research, that is the evidence-weighted concern, not a secret caldera, a known gap. And known gaps are dangerous because they often sit quietly until the day they matter. Everyone agrees the system should improve. Then budgets compete, priorities shift, public attention moves on. The last disaster becomes history. The next one has not happened yet. The work continues, but not always at the speed the hazard deserves. That is how readiness gaps persist. Not because nobody cares, because rare hazards are hard to keep urgent. This is especially true when the hazard hides underwater. A land volcano can become a national symbol. People can see it, journalists can film it. Evacuation maps are tied to a visible mountain. Submarine volcanoes lack that emotional anchor. There is no skyline, no smoking summit, no daily reminder. The ocean covers the evidence. And when the evidence is covered, the public imagination goes blank. That blank space is the problem. Because if people do not imagine a volcanic tsunami, they will wait for the wrong warning sign. They will wait for shaking. They will wait for a familiar alert. They will wait for someone else to be certain. And a near-source wave may not give them that time. So the evidence-weighted message is this. Do not panic about an unverified eruption. Do update the mental model. Not all tsunamis start with earthquakes. Not all warnings begin with shaking. Not all dangerous waves look large at first. Not all volcanic hazards are visible from shore. That is the lesson. Interpretation 3. The concerning sealsing, the most concerning interpretation is that another Hunga class, or smaller but closer volcanic event occurs before the warning system and public education have fully adapted. This is not a prediction, it is the ceiling. And the ceiling does not have to be global to be disastrous. A moderate volcanic tsunami close to people can be worse than a larger far-field signal with hours of warning. A collapse near a populated island can be more deadly than a basin-wide anomaly that gives warning centers time to react. A local harbor surge can kill if people walk toward the water. In this version, the eruption source is close. The mechanism is complex. The first signals are ambiguous. The public does not feel a major earthquake. The warning center has to interpret volcanic, oceanic, and atmospheric data quickly. Local communications are imperfect. The first wave arrives before full understanding. That is the nightmare. A disaster in the gap between detection and comprehension. What would push us toward that ceiling? Official reports of major submarine eruptive activity. Rapid changes in sea level near the source. Dart or tide gauge anomalies. Strong hydroacoustic signals. Satellite evidence of a major plume or surface disturbance. Reports of collapse, landslide, or sudden bathymetric change. Tsunami bulletins from recognized centers. That is what to watch. Until those signals exist, the concerning ceiling remains a possibility, not a forecast. That distinction is not optional. It is the difference between vigilance and fear-mongering. What we should watch next here is the practical watch list. Watch Smithsonian's Global Volcanism Program for confirmed eruption reports in the Tonga-Kermadec region. It maintains eruption information and regional volcano records, including current continuing activity listings. Smithsonian Global Volcanism. Watch GNS Science for New Zealand and Kermadec region science, especially when activity involves the Kermadec Arc. Watch Tonga Geological Services and Regional Pacific Emergency Agencies for local bulletins. Watch NOAA and the Pacific Tsunami Warning Center for tsunami information statements, advisories, watches, and warnings. Watch UNESCO IOC work on volcanic tsunami guidance, because that is where the system-level recommendations are being formalized. Watch NASA Earth Observatory and satellite-based reporting when submarine eruptions produce surface changes, new islands, plumes, or pumice, and watch the human system. Because the best sensor network in the world cannot save people who do not know what the message means. Every tsunami-prone community should know its evacuation route. Every school near a tsunami coast should drill. Every harbor should understand that strong currents can last long after the first wave. Every tourist region near volcanic arcs should teach visitors that tsunami warnings are not only earthquake warnings. Every family near a low coast should know high ground. And every person should know this sentence: if the sea behaves strangely, leave. That simple sentence should be remembered before any siren, bulletin, model, map, or explanation arrives later. Not after the video, not after the explanation, not after the perfect official confirmation. Leave. That is not panic. That is respect for the clock. The closing case. So, where does this leave us? The eruption in the title has not been verified. The secret awakening caldera has not been confirmed. A basin-wide stealth tsunami is not guaranteed tonight, and I am not going to tell you otherwise. But the hazard class is real, the Tonga-Kermadec arc is real, the submarine volcanoes are real, Hunga was real, the tsunami was real, the atmospheric pressure waves were real, the monitoring complexity was real, and the call for better volcanic tsunami warning procedures is now written in international guidance. GNS science, that is enough. The deeper lesson is that the modern world is very good at seeing some dangers and surprisingly vulnerable to others that arrive through the gaps between categories. Hunga was not only a volcano story, it was not only a tsunami story, it was not only an atmospheric story, it was all of those at once, and that is why it unsettled so many assumptions. Categories help us prepare, but nature does not have to respect them. A volcano can disturb the ocean. The atmosphere can push the sea surface. A local wave can become a regional problem. A small first arrival can hide a larger later danger. A source that is invisible from shore can change the life of everyone standing on that shore. When hazards cross categories, institutions have to communicate across categories too. That is the real meaning of not ready. It does not mean helpless. It means the adaptation is unfinished. The instruments are improving. The science is advancing. The guidance is being written. The memory of Hunga is still recent enough to teach. But public imagination often changes more slowly than hazard science. People keep the old story because it is simple. Earthquake, shaking, tsunami. The new story is harder. Earthquake or landslide or eruption or collapse or pressure wave, visible or hidden, near or far, obvious or confusing, with the sea itself sometimes giving the first warning. Harder does not mean impossible. It means the message has to be repeated until it becomes simple again. Not all tsunamis start with earthquakes. The first wave may not be the largest. Strange sea behavior is a warning. Move inland or uphill. Wait for the all clear. Practice before the day you need it. Those sentences are not dramatic. They are survivable. We do not need a fake secret to make this frightening. The published facts already do that. A volcano under the ocean can disturb water in ways people do not expect. A tsunami can arrive without the earthquake people are waiting for. A warning system can work and still be incomplete. A community can survive because it is practiced or suffer because the first minutes were spent trying to understand what kind of disaster had begun. That is the lesson Hunga left behind. Not that every underwater volcano is a monster. Not that every caldera is a countdown. Not that every hydrothermal plume is a warning. The lesson is quieter than that.
The ocean can hide the beginning. And when the beginning is hidden, readiness has to come before certainty. That is the uncomfortable part. We like certainty because it feels responsible. We want the official message, the final map, the clean mechanism, the expert statement that tells us exactly what happened and exactly what comes next. But disaster often begins before the explanation is complete. A wave does not wait for the paper. A coastline does not wait for the model. A harbor does not wait for a press conference. So the practical truth is simple. Know your coast, know your route, know your warning signs. Know that not every tsunami begins with shaking. And know that if the sea suddenly stops behaving like the sea you recognize, you do not owe curiosity one more second. You move. Because the next warning may not start under your feet. It may start under the ocean. And by the time we can finally see it clearly, the water may already be on its way.